Hello all. So today I'm going to discuss a binary search problem which is going to be applied on an unsorted array. Okay. So basically the problem statement is like given an unsorted array of integers, we need to find the element at the kth index position in its sorted format. So uh, what problem is saying is we are given an unsorted array. Let us just consider this is an unsorted array. So once we sort this array, right. So we will be also provided with a kth index element, like a k index, which like we can say it is 4. So we need to find what element will be coming at index 4 when this array is sorted. Okay, so when this array is sorted, what element will be coming at its fourth position or fourth index. So based on array indexing which starts from 0, so we need to find the element at the fourth index when this array is sorted. So one condition which is also given in the statement is that you cannot modify the original array. So whatever original array is being given to us, we cannot modify that array. So let's just consider a brute force approach what we can do. So one thing which comes to the mind is like we need to find the kth index position in the sorted format. So let us just sort the array. But since we cannot modify the original array, so we will store the sorted result in an other array in a certain like in other variable or other array, and then we will find return the kth position, which is the easiest way to deal with this problem, right? So let us just go ahead and implement that. So here is the editor. So let me just consider the array, feed this from here. Okay, so these are elements. K is 4 for us. Okay. So now we need to store the sorted format of this array, right? So let us just consider our sorted array, which will basically store the sorted result of this array A. And ultimately, we are going to return what? In this sorted array, we need to find the kth index. So we just return the kth index, right? So this is going to give us correct result ultimately. If we run this array, uh, oh, there's double equals to sorry for that. Yeah, 18. So what it states is that when we sort this array, we will get 80 as its fourth position. So let us also print the sorted array to clear it for us. Here it is. So as you can see in the sorted array, 18 is coming at fourth index starting from 0. So 0, 1, 2, 3, and this is fourth. So it is giving us the correct result. But what is the drawback of this thing? Like, what is the time complexity? Let's just consider the time complexity and the space complexity for this brute force approach. Okay. So if we head back to the document, so what we did, we first sorted the array, sorted the array, which ultimately took us n log n, even implementing the inbuilt sort function, and then we stored the result in a separate array. Stored result in separate array, right? So it also costed us a certain space complexity here. So the time complexity for this algorithm is going to be n log n, whereas the space complexity costed us n because we stored the sorted result of this array in a certain separate array. So for each input array, we are going to sort it and store it in a separate space. So we are going to take space complexity of the size of the array, that is n. So can we optimize this space complexity somehow? Right. We need to look into that direction. Like, can we optimize the space complexity? Because somehow we are going to sort this array in order to find the element at this kth position, right? So sorting function, if we consider merge sort or quick sort, they like merge sort average scenarios, best case scenarios and log n, or even the worst case scenarios and log n. So basically, we need to ultimately sort the array in somewhat fashion and then get the result. But can we optimize the space complexity? So then comes into the picture the optimized approach, which is the binary search. So binary search comes to the rescue here in actually optimizing us the space complexity for this, for this problem. So let's see how we can actually utilize binary search here. So two things to consider while applying binary search. One thing is the target, and the second is the search space. Okay. Target is basically what we're trying to find from a problem, right? And the search space is basically in what will be a search space, like in what area are we going to search for our target. So that determines the search space. So from the problem statement, we can clearly say the target is the kth index position in its sorted format, right? So it is very obvious, like the target for us is the kth index element in the sorted array, the kth index element. So the kth index element in the sorted array is the target. Now, what can be a search space, right? We can say that the kth index ultimately is lying. The index will be lying within this array itself, right? Whatever the index is going to be, it is going to lie within this array itself. Between 0 to, let's say, how many elements are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, so 0 to 8, we can say our index is lying to be going to lie within 0 to 8th index. But can it help us somehow, like taking the source space from 0 to 8? Will it be able to help us? How can we discard, by considering only the indexes as our search space? How can we discard a certain half of the search space? Because binary search is basically discarding a certain half of the search space so that we can consider the other half. So how can index actually help here? Basically, answer is no. Like index cannot help here. Like if you would try it yourself and try to look into how can we optimize or find any algorithm based on that index, even if we consider, let's say the index is 0 and the last index is that is 40, right? So we consider left index to be 0 and right index to be 8, right? So the middle index would be 0 plus 8 by 2, that is 4. So now when we are here, like 0 1 2 3 0 1 2 3 4, when we are here, can we make any conditions or deductions from here, like for this element, whether this element is going to be our kth like the element at the kth index position or not? Can we find any condition in which we can actually decide where to sort or which half to discard in this array? We cannot, right? We cannot decide here by just taking a search space as the index is. We cannot discard a certain search space. So let us just consider a second different search space, right? So what can be a search space? The second thing is, like, we can consider, as we know that there are certain number of elements here. So definitely when in the sorted format, right, the element which is going to come at the kth index position, hear me carefully, the element which is going to come at the kth index position will ultimately be an element from this array, right? It will be element from this array itself. And other thing is, like, that element which is going to lie at the kth index position, the element will be within the range of the minimum element of this array and the maximum element of this array, right? So the two things, right? One is that the element is going to be one of these elements itself of the array, because ultimately we need to return an element from this array which is going to be found at the kth index position. So one thing is that, right? First thing is the element is going to be one of the elements of the array, right? Now the second thing is that the element is going to lie between the minimum and the maximum element in the array, right? We can say that, right? Because the minimum element, let's say, that is 3 and the maximum element, that is 4. So ultimately we can say that all the elements which is currently present in this array are either greater than 3 or either they are less than 40, right? All the elements in this array are either greater than 3 or less than 40. So those that element which is going to lie at the kth index position is either going to be greater than 3 or less than 40. Right. So from these two things, we can say that our search space is actually going to be, if you guessed it right, it is going to be lying between the minimum and the maximum element of the array ultimately, and it is going to be one of the elements, right? So let us just consider what is the minimum element is that is 3. So we will take up one like that is 3. The right, we will initialize the right variable, which is going to be the maximum element in this array, that is going to be 40. I hope you must be knowing like how to find the minimum and the maximum element. It is just going to take a single iteration to actually find this thing. Now, now the mid. Now we are going to calculate the mid. So now the mid is going to be the element itself, right? So what we are going to do is basically once we have now decided the target and the search space, now what we can say about the kth index element. Once we sort this array, right, as if we consider here, once we have sorted this array, we know that for every index, like let us say that for 4 we need to find, for k equals to 4, we need to find the element at this position. So for any index, we can say that the smaller element count is going to be equivalent to that index, right? For example, for k equals to 4, for k equals to 4 in the sorted format, we can say that the element which is going to lie at the fourth position in the sorted format is going to have that number of elements smaller than it, right? For example, if k equals to 3, so I can say that I need to find an element which is having 3 smaller elements from it in this array. Right. Let if I consider any target, if I consider any element like that, let's just say that it is x. So for element x to be lying at position 3, we need to find the number of elements which are smaller than x in this array. Right. Like for example, in this brute force approach for index k equals to 4, we found 18. So considering 18 as our x, what we are doing is, what we are actually observing is that for 18 there are 4 elements which are smaller than it, which is equal to k. Right, there are 4 elements which are smaller than 18, which is equal to k. So this is going to be a condition by with which we can actually decide or discard a certain search space, right? So this is going to be the condition by which we are going to actually discard our search space. So let us just say that how we are going to calculate the mid, we are going to add left plus right and by 2. So that is going to be 43 by 2, which is equal to 2 and 1, 21. Right, 43 by 2, that is going to be 21. So now we are going to find smaller element count in the array which is smaller than 21. How many elements are there actually which are smaller than 21 in this array? How it is going to help us to compare, like if the elements are smaller than, like if there are k elements smaller than 21, we can say that okay, 21 can be an element which is actually present in this array, and also in this sorted format is going to come at the kth position, that is 4. So let us just see, right, for 21 let's just see that how many elements are smaller than 21. So here we can say that there are 1 2 3 and 4 elements smaller than 21 in this array, right? There are actually 4 elements smaller than 21 in this. I hope I am doing this right. 1 2 3 4, sorry, 5 elements, sorry sir, 5 elements are smaller than this array in this, right? So there are 5 elements which are smaller than this element in the array, and our kth target, let us just consider it is 4. So 5 is actually greater than 4, right? 5 is actually greater than 4. So what it states, it states that this element cannot be our kth index element because it is having more elements which are smaller than it. So it is ultimately going to lie further, or you can say at index 5 or 6 in the sorted format of the array. So we need to go where? We need to go left, or we need to decrease this value so that the count of elements smaller than the mid also decreases. So what we are going to do, we are going to decrement right by mid minus 1. So we are going to take it as 20. This is going to remain as 3. Now it is 23 by 2, which is equivalent to 202 to 6, 12. Right. Now we are going to consider elements which are smaller than 16. So let us just go consider this array. So we are having 4 elements which are actually smaller than 16. Right. So we are actually having 4 elements here. So can we say that this is equal to 4? So we can say that this element is one which in its sorted format is going to lie at index 4. Right. But we need to find an element which is also one of the elements of the array. Is 16 one of the elements of this array? It is not, right? But it can be one of the answers, right? So we will store this answer here, but we will continue to search, right? We will continue to search for this element. So what we will do is we will going to increment our left by mid plus 1, that is 70. So why we are doing this? Because we are going to find the upper bound of this element of this position, because ultimately 6 is the minimum element we can say. If we further go smaller than 16, we are going to decrement the small element count. So we are going to consider the upper bound. So that is why we incremented it. Right. So now here it is 7 and 2 plus 1 3, 37. 37 by 2. So what is going to be 37 by 2? 2 ones are and 1 7. 8, 18. So let us just consider how many elements are actually smaller than 18. It is 1, 2, 3, and 4. Right, again, we got the 4 answer. So we can also again store this answer. And since we cannot justify that all, like if it is even present in the array, so let us just consider the upper bound. Right. So we will again increment left by mid plus 1, that is going to be 19. And the right is going to be 20. Right. So one thing to also consider here is the breaking condition, right? So till the time left is less than my right, right? Till the time my search space elements are like the left condition is less than equal to the right, I'm going to continue in this array. So 20 plus 19, that is going to be 39, which is ultimately dividing by 2. It is going to give us what? 2, 1 and 19. So how many elements which are smaller than 19? We can see from here there are 5 elements which are smaller than 19. So it's actually incremented, right? It actually incremented. So now since we have it incremented, so we are going to decrement our right by mid minus 1, that is going to be 18. Right, mid was 19, we decremented at moment minus 1, that is going to be 18. This is 19. Now our left is greater than right, so we can clearly break here, and the answer is 18 as per the binary search. Let us just implement it once and do the dry run again, and you will understand it much more better. So what we are going to do here is, okay, so let us just consider a function first, like a count. Okay, so let us just do one thing first. Let us just initialize our variable, that is left, which is the minimum of the array, and right, which is the maximum of the array. Okay. Now while my left is less than and equal to right, I'm going to calculate the mid, which is going to be left plus right whole divided by 2. Now the condition is like if my sorry, now we need to find the element which is smaller than me. Count smaller, because this count smaller is actually going to return my index value, right? For this mid element, what is the index value? So let us just implement this function, right? Self dot count smaller element. I'm going to pass in the mid and the array. So now this counting the smaller elements, right? This is going to be a linear way of doing this thing, right? We can only apply the linear search here because this array is unsorted. So to return the smaller element count in the array, we are just going to implement a linear search of elements and return the count of smaller elements. So for value in array, if my value is less than the mid, right? The mid element which I have considered, I am going to increment the count, and I'm going to return that count. Okay, I'm going to return that count. So now I'm going to get the count of smaller elements. Now I'm going to compare that if this count smaller is less than or equal to my kth index position. If it is, I'm going to increment by update my answer by mid, and I'm going to go and find upper bound. I'm going to increment my left by mid plus one. Else, if my count is greater, right? Ultimately, if my count is greater, if my count was greater, so I needed to search for elements which are smaller than the current element. So I decremented my right by mid minus one, right? I decrement my right by mid minus one, and at the end, I can simply return the answer, right? Let's just consider my answer is minus one, and let me just bring them down as well to make it more clear. So my answer is minus one. My left and mid, the left and right are have been initialized, and now we are going to find the answer, update the answer with this and print. So let us just see if this works or not, right? Let me just also binary search. Let's just see if the binary search is actually giving the correct answer or not as per our brute force approach. Okay, so let us just run this. Self is not defined. Oh, right, that self. Okay, so this is not array. This is going to be A because we consider A as another array. Okay, right. So both the approaches gave the same result. Okay? If I, let's just say one. Let us just consider one. We can also optimize this, right? Since like it gave us 5. So as you can see in the sorted array, brute force is also giving 5 and the binary search also gave our result as 5. You can also optimize this slightly by considering the edge cases. For example, what if k's value is equal to 0? If k is 0, then we ultimately need to return the minimum element because in the sorted format, the minimum element is the one which is going to lie at the 0th position. Right, so we can ultimately prevent us from running this complete thing and we can just return that answer. Apart from that, if our kth value, kth index is actually the maximum index of the array, right? If it is the maximum index, let's just say that if it is 8 or in the current scenario, so we can ultimately return the maximum element here, again preventing us from running this complete loop. Right. Those are just small optimizations which we can do and which can return our answer in n time complexity itself. Because finding the confirming that the kth index element is actually equal to the length last index of the array, we need to know the length of the array first. And ultimately, to find the length of the array, we will need to apply the brute force approach for that. So it can provide a slight optimization, but ultimately the major takeaway from this thing is that we optimized our space complexity. If you would see, like, if are we taking any extra space here? We are not. We are just initializing two variables and a answer variable, and we are just finding it using the binary search approach, and we are returning that answer. We are just only initializing certain variables, right, and just returning that answer. So no extra space has been taken to store the sorted array. Whereas in brute force approach, were storing a sorted array in an extra array, right? And other thing to consider is the time complexity. So like for binary search, right? For binary search, we can say the time complexity is always what? Binary search. For binary search, what is the time complexity? It is going to be n log, right? My computer is very slow. Sorry. So for binary search is going to be log n, right? Because we are always what we are doing. We are always discarding a certain half of the array and searching in the other half. you can say. The search space is what? It is actually from 3 to 4, ranging from 3 to 4. Our search space is ranging from 3 to 4. So what we are doing here is, once we consider the middle element and we say that it is not our answer, we decrement our right or we increment our left. So if you would carefully look here, we decremented our search space from 3 to 20. So what it is actually is, we decremented our search space. We discarded from 21 to 40. We discarded this search space and we consider the search space from 3 to 20 itself. Right. And again, in the next time, what we did was we discarded certain other search space. We incremented our left from 16%, that is 7 to 17. So we discarded a search space from what here? We discarded a search space of 3 to 16. Right? We discarded a search space from 3 to 16 and we consider what? Now we consider from 17 to 20. We consider this search space. So we are always discarding a search space by half. That is why time complexity is log n. Now, binary search is working in log n, but is this count smaller working in log n time complexity? No. The count smaller is basically taking n time complexity, iterating over each and every element of the array to find the smaller count. So for every binary element, right, for every mid, we are calculating the small element count, right? For every mid element, we are calculating the smaller element count. So we can say we are doing for every log n, we are doing what? We are iterating the array again. So the time complexity for this optimized approach is going to be n log n. This is the time complexity. And the search space or the space complexity is going to be constant. So we optimized our time complexity from n log n and n, which is a space complexity, to the time complexity, which is n log n, and the space complexity that is constant. We optimize the space complexity here using the binary search. So I hope you learned something from this, and let me know if somehow I can also, make it more explainable to you and more easily understandable for you. Thank you and have a great day.